We're in section 3.2. This is actually going in a different direction than we were in 3.1, and we are combining functions. So we have to go through a little bit of vocabulary to start off. The first vocabulary word, which you may or may not know the definition to, is variable. If you are identifying the variable in a math sentence, you would be identifying the spot that has a placeholder. For instance, if you saw this math sentence here, this happens to be an equation, the variable is x. It's the placeholder in a math sentence. Sometimes you'll see an expression. Variable here, again, is x, the placeholder. And then you have the constant. Again, in a math sentence, it's a number that's by itself. So if I bring this example again, the constant, actually I'm going to make this an expression. The constant would be 5. That is not attached to a variable. That means that no matter what I plug in for x, it's going to change the value of this term, but this term is always going to stay 5 because it's constant. It doesn't have a variable next to it that's going to change its value if you plug a number in. Then we have the word term, which I've already been using to describe other things. The most fundamental component of a polynomial is a term. It can either be a number, variable, or a combination of numbers and variables multiplied together. So a term can look like this. It can look like 10x squared. It can look like 5xy cubed. It can look like 6. These are all terms, and terms are separated by plus signs and minus signs. So if I did this here, we would say that this is 3 terms. A polynomial is any combination of terms that are added together. The powers of all the variables on the polynomial must be positive integers. Okay. So a polynomial, really, it's like a math sentence. For instance, right here, this is a polynomial. Notice that the exponent is a positive number. Things that would make an expression not be a polynomial is if it has a term and the term has a fraction. You can't have a term that has a fraction with a variable in the denominator. For instance, 3 over x. Something like this cannot be part of a polynomial. And then another one is if a term has a square root symbol with a variable underneath, then it is not a polynomial. So there's lots of things that can be polynomials, but if you see a term that has something where there's a fraction and there's a variable on the bottom, or it has some kind of rooted part of it that has a variable under the radical symbol, then it's something, but it's not what we would consider a polynomial. So let's look at some examples. Determine whether the given expression is a polynomial, or if it is not a polynomial, and explain why not. So I have a 3-term expression here. This is not a polynomial because there is an m under the radical symbol, not a polynomial. B, there's 2 things I'm looking for here. One of the things I'm looking for is to see if there is a radical symbol that has a variable underneath it, or if there's a fraction that has a variable on the bottom. This is a polynomial because neither of those 2 cases are happening. Looks great. C, not a polynomial, and that's because if you look at this second term, there is a variable under the fraction symbol. Last one, we're going to talk about coefficient. This is the numbers in front of the variable. I'm going to use kind of a parentheses s in a polynomial. For example, if you have 5x to the 5th minus 2x squared plus 15, the things that we would call coefficients are the 5 and the negative 2. Coefficients are in front of variables. So in this case, it's 5 and negative 2. There's two coefficients because there are two terms that have a variable. Notice I didn't say anything about the 15 because we call this the constant term. And if it's a constant term, it's not attached to a variable, and it's not attached to a variable, then it can't be a coefficient. That's a thing. Let's go to the next page. Second page, we are looking at vocabulary a little bit more. I have to warn you that I have a little puppy in the background that is quite loud, so hopefully it won't be too much of a distraction. So looking back at polynomials, which we've just got done describing, there are actually some specific polynomials that have specific names. For instance, a monomial that has the prefix mono means that it is a one-term polynomial. So a monomial can look like this. It can look like this. It's just one term. These are two separate ones. So I'm just going to kind of put a little bracket here so you can see that I'm not putting these together. A binomial, bicycle, two-term polynomial. An example for that would be like 5x plus 8. There's two terms. Or 6x squared minus 2x. Two terms. And then the trinomial is a three-term polynomial. And you'll see these quite often. Usually there's second degree ones. X squared plus 3x minus 1. There's three terms. 1, 2, 3. Here's 1, here's 2, here's 3. After that, polynomials are just called polynomials. If somebody called this monomial a polynomial, they wouldn't be wrong. It's just a more broad name for it. If you wanted to give a specific name, monomial, binomial, and trinomial, those are specific names for 1, 2, or 3-term polynomials. One thing that you would be doing with polynomials is being able to find the degree of a term. And the degree has everything to do with your exponents. Now, this is kind of blurry, so I'm going to write these in. What you have to do to find the degree of a term is add up the exponents. So for this first example, the degree of the term is 5 plus 2, which is 7. The second example, you have 2, 12, and even though there isn't one right here for the z that you can see, you write the 1 in there. So this is a degree of 2 plus 12 plus 1, which is 15. We call that a 15-degree term. Really interesting, right? So you can find the degree of a term, or you can find the degree of a polynomial, which basically means that you're going to find the degree of every term. In this case, the first term has a degree of 2. The second term has a degree of 1, and the third term has a degree of 0. The highest degree is the degree of the entire polynomial. So this polynomial has a degree of 2. Yep, squeaky toy. For B, the first term is a first degree term, the other one is 0, so this is a degree of 1, the highest number. For this next one, we have 3, 2, 1, and 0. So the degree of this entire polynomial is 3. On page 54, we're looking at the idea of terms that are like terms or not like terms. If you have more than one term that share the characteristics of having the same variables and exponents, then we can call them like terms. Here's an example of a set of like terms. Here is another example of like terms. Notice that the squaring is only with the x. Their set of variables and exponents are exactly the same. Here is another example. It doesn't matter if the number is negative or positive. The only thing that matters is that this stuff here is exactly the same. We would call those like terms. Terms that are not like terms have different variables. So for instance, 5x and negative 3x squared, those are not like terms because one has a squared and the other one doesn't. Or if I had 10x squared y and 3xy squared, these are not like terms because the squaring is with the wrong variable. It's not exactly the same. And the whole thing with like terms is they can be combined by adding and subtracting. So this is a thing that's kind of important. If you are going to be adding and subtracting and simplifying expressions, you need to know which terms can be combined because they're like terms and which ones cannot. So let's look at A. I have a binomial combined with another binomial. They both have a set of parentheses around them. Anytime you have a set of parentheses and you're not sure what to do with it, you can put a 1 in front and distribute whatever is in front to get rid of the parentheses. In this case, anything multiplied by 1 is itself. So I can actually write this out without the parentheses. And then I'm going to identify what terms are like terms. For instance, I have an AB squared here, so I can simplify that by combining it with that last term. There is no other terms that have a b, and there is no other terms that are a squared b, so I'm going to leave those the way they are. I combine these by adding the coefficients, so I have 5ab squared plus 5b plus 4a squared b. We simplified this by combining like terms. The next example is a little bit more challenging because not only do you have the set of parentheses, but they are being subtracted from each other. So for that first set of parentheses, I am distributing a positive 1. And for the second set of parentheses, I'm distributing a negative 1. So I have negative 3x squared plus 5x minus 3. This negative changes all the symbols of each term inside those parentheses. Now, if I look here, x to the fourth, I don't have any other terms that are like that, so that's going to have to stay by itself. Then I have an x squared term. Here's an x squared term. I have a x term. Here's an x term. And then I have my constant. So if I write this out, x to the fourth is going to be my first term. I'm combining my green terms. Negative 3x combined with a negative 3x is negative 6x squared. 4x combined with a 5x is 9x. And then my constant is at the end. So after I have simplified by combining like terms, I'm left with a 4-term polynomial. Multiplying polynomials is a little bit more tricky. And we have lots of different methods that I've learned through the years. A lot of people have learned through the years. We can use what we call double distribution, also formerly known as FOIL, or the box method. For instance, if you have a binomial times a binomial right here, and I do double distribution, it means I'm distributing my first term to each of the terms in the second binomial, and then my second term gets distributed. If I distribute my first term twice, the result would be 2 terms. And if I distributed the second term twice, that result would be 2 terms. So I'm expecting that after doing some multiplying and distributing, I'm going to have 4 terms, and even furthermore, I might be able to combine some of them to simplify after I'm done. So if I have 2x times 4x, that's 8x squared. 2x times negative 8 is negative 16x. 5 times 4x is 20x. And then I have positive 5 times negative 8, which is negative 40. I can combine these two middle terms because they are like terms. So I'll have 8x squared plus 4x minus 40. And that's just using the double distribution method, which is basically multiplying each piece of the second binomial by each piece of the first binomial. The box method is pretty simple. You have to recognize how many terms you are multiplying by in each set of parentheses. This is 2 terms being multiplied by 2 terms, so I need a 2 by 2 box. Here's my 2 by 2 box. I'm going to go ahead and write on the outside of the box x plus 3, that's the first binomial, and then x minus 4, that's the second binomial. And what I'm going to do is use an area model to fill out the inside of my box. For instance, x times x is x squared, x times 3 is 3x, x times negative 4 is negative 4x, and negative 4 times positive 3 is negative 12. each time I had to line up what the top of the box was with what the side of the box is and multiply them. These are the four terms that I have: x squared minus 4x plus 3x minus 12. I can combine those two inner terms to get the answer, which is x squared minus 1x minus 12. This last one, you can still do double distribution if you want to, but notice if you have three terms here, that would mean that after distributing the x and distributing the 2, I'm going to end up with 6 terms before I start combining like terms. This is a much easier problem to do if you create a 2 by 3 box. 2 by 3 box. The box method is definitely welcome here. It keeps everything very tidy. I'm going to make sure I put my trinomial across the top because it has enough boxes to accommodate it. My binomial is going down the side. And then I'm going to go ahead and multiply to fill out the inside of my box. Notice that like terms in this case are diagonal from each other. This is kind of interesting. I could probably combine those as I come down. I have x cubed plus 5x squared minus 1x minus 14. Notice here that I was adding the 2 and the 3 to get this. I was adding negative 7 and 6 to get this. And I have a 4-term answer. What I did on this last page is I just found this. I thought it was nice and tidy. If you have a hard time remembering the box method, here's just a little bit of a graphic for you to reference if you want to see it written or shown by another source. So that's just there for your to add to your toolbox of resources.